So if you've already performed the dilation of scale factor 1/2 to get from A to A prime, what would you have to use to get back from A prime to A? So if you went half the size to get back, you'd have to go double the size. So the scale factor would just have to be 2. You can always undo a dilation by doing the reciprocal. So since it was 1/2, you just flip it to be 2/1. So if A prime, B prime, C prime is the image after a dilation of scale factor 3, that means that A prime, B prime, C prime is 3 times larger than ABC was. But dilations do keep them similar. So that's our first statement. And when figures are similar, all of their angles, their corresponding angles, will be congruent. So the measure of angle A is the same as measure of angle A prime. Measure of angle B is the same as measure of angle B prime. And the measure of angle C is the same as measure of angle C prime. But the side lengths are not the same. So when it's talking about A prime, B prime, the side length, if this had a length of 1, since it was a scale factor 3, A prime, B prime would be 3 times that much. So A prime, B prime is 3 times as much as AB was. Similar, B prime, C prime is 3 times as much as BC was. And A prime, C prime is 3 times as much as AC was. So graph the triangle, and we're going to do a dilation of 1/3 from vertex A. So -3, 4. -2. And C is -2, -2. So there's the triangle. If we are doing the, well, here's the triangle. If we are doing a dilation with scale factor 1/3, that means all the side lengths will be 1/3 the size of what they were. The easiest way to figure that out is just to count from vertex A how far you'd have to go to get to one of the other vertices. So go from A to C. It goes down 1, 2, 3, 4, 5, 6, and over 1. It goes down 6 and over 1. You have to do 1/3 of that. So you multiply by 1/3 or divide by 3 to both of those numbers. That tells you how much you're going to be changing from A to get to C prime. So 6 times 1/3 is 2. 1 times 1/3 is 1/3. So what that means is, since we before we were going down 6 over 1, now we're going to go down 2 over 1/3. Down 2 over 1/3. And that will be the coordinates of C prime. You do pretty much the same thing with B. To get from A to B, you have to go down 6 and over 4. But the dilation, the scale factor, is 1/3. So you do 1/3 of that and 1/3 of that. So instead, we're going to go down 2 and over 4/3, which is like 1 1/3. So you go down 2 and over 1 1/3 to get B prime. Graphing them is pretty easy. Now you have to write the coordinates. Now A prime didn't move because A prime was our center. So that's also A prime. So A prime is still the same as A was. B prime's over here. You have to get those coordinates. So remember, we only went a third. That's not a half, that's a third of the way. So that's -1. Well, we're actually -2, but we're a third to the right of that. We're a third to the right of -2, which is like -6/3 plus 1/3. That's our x coordinate. And our y coordinate we can see is 2. We have to do pretty much the same thing with C prime. We went 1/3 to the right of -3. 1/3 to the right of that. So that's the same thing as saying -9/3 plus 1/3, which is -8/3. And then our y value is 2. On the triangle similar, pretty simple question. They have a 90-degree angle. They each have a 30-degree angle. So the two right triangles, they each have a 30-degree angle. Yes, they're similar because of angle-angle. They have two angles that are the same. They have the right angle and the 30-degree angle. So construct the midsegment. So that means we need 2 midpoints. So you can pick whichever sides you want. I'm going to choose to do the midpoint of HO. So you put your point of your compass on the vertex, stretch it more than halfway, make a semicircle. Do the same thing from the other vertex. That line shows you the midpoint. Then we're going to do the same thing from T and H to get that midpoint. So make sure it's stretched more than halfway. It is. Change colors. So now we have our intersection there. So get the line to find the midpoint. So that's our midpoint right there. So we have our 2 midpoints. You can connect them, and that is the midsegment. So you can call those 2 points that we created whatever we want. We haven't used A and B, so I'll just use A and B. So to write a proof, we have our statements and reasons. Now, whatever we constructed, that's what we're given. So we know that AB is a midsegment. So that means that HA is congruent to AO, and HB is congruent to BT. For both of these, it is definition. Mid-segment is the midpoints. So we then have the option to either show that since those pieces are congruent, the ratio is the same, which means that these sides will be parallel. Or I think it's a little bit quicker if we show that the ratio of HA to HO is the same as the ratio of HB to HT. So whatever this length is, if this length was 1, then HO would have a length of 2. It would be double, because it's just 2 of the same segment. HB to HT, that would also have a ratio of 1 to 2. So really all that it's saying, and I'm going to just use this, that 1/2 equals 1/2. True statement. It's kind of the reason, because the ratio of HA to HO is 1 to 2. A few different ways you could word that. I'll just go with that. So we've got the sides then are proportional, HA to HO and HB to HT. We also have this angle up here at H. Congruent to itself, and it's in both triangles. Congruent to itself means reflexive. That's the reflexive property. So we just showed that the two sides are proportional and the angle between them is congruent. Therefore, the two triangles, HAB are going to be similar, HAB and HOT. And that was the two sides were proportional and the angle between was congruent, so that's side, angle, side, similarity. Officially, there's a few steps that we're kind of skipping over in here, but I think the idea is understood if you just jump to that. Why are the two triangles similar? Is it angle, angle, side, angle, side, or side, side, side similarity? So just look at what we have. We have a 30-degree angle matches with a 30-degree angle. We have 70-degree angle that does not match with an 80-degree angle. But for three angles of a triangle, always add to 180. So if this is 80 and 30, we can figure out that this angle over here, that would be 110 if you add them together. So with some subtraction, 180 minus 110, the third angle is 70, which means those two angles are also congruent, so we have angle, angle. Likewise, you would have found that 30 plus 70 is 100, so this angle would have been 80. You could have done that to get angle, angle. For this other set, we have vertical angles here. We don't know any more angles, though, so it's not angle, angle. We do have some sides, and it looks like they're proportional. 2 over 3, those sides would match up. 4 over 6, they both reduce to 2/3, so yes, they are equal, which means We have side, angle, side. We have the two sides with the angle in between. Is triangle XYZ congruent or similar to triangle SRZ? So XYZ on the left, SRZ on the right. They're definitely not congruent. They're going to be similar. And the reason they are similar is we have these parallel lines right here, which means if you trace out the Z shape for alternate interior angles, you get those two angles are congruent. You can trace out the other Z shape to get the other two, or you can use vertical angles right here. So we have two angles are congruent, which means all three angles are congruent, so it's angle-angle similarity. Then to find the value of x, you have to write your proportion and solve it. So when you write the proportion, make sure you take corresponding side with corresponding side. So that means that the 12 between our two markings we created goes with the 9 because that's between the two markings we created. And we took the triangle on the left first, so in our next fraction we take the triangle on the left again, 16, with its corresponding side, which is x. So cross multiply, you get 12x equals 144. 9 times 16. Divide by 12, you get x equals 12. This question came from section 12.4, the last lesson of the framework. It says that the segment in the middle, squared, is equal to the two pieces multiplied together. So multiply 18 times 12 is 216. And then the square root of 216 if you were to round that, it'd be about 14.7. So true or false, all rectangles are similar? Well, no, you can have a short and fat, or a little bit taller and just as fat. Those would not be similar. You could also have really, really, really skinny and really, really, really wide. Those are not similar. So no, false. How about all squares? Well, we know all four angles would be the same, and all the sides would have to be the same length. So even if you had different sized squares, the ratio of the sides, since the sides would all be the same, it would be a 1-to-1 ratio for all the sides. So yes, they are similar. Isosceles triangles. Well, isosceles triangles can be really tall and skinny or really short and fat. Those would definitely not be similar, so false. Scalene triangles, that could be a lot of different things. You can have an obtuse scalene triangle. Or you could have a scalene triangle like this, which is an acute scalene triangle. They're definitely not similar. Now, equilateral triangles, pretty much the same thing as squares. There's really only about one way to draw them. Because all three sides are congruent, just like with squares, and all three angles are 60 degrees. The 60-degree concept is actually enough because we know angle. If two angles are the same in the triangles, they have to be similar. So we have 60-degree angles in all equilateral triangles, so that's true. Right triangles do not need to be similar, because you can have some that have the sides that are the same length or close to the same length, and then you can have some that don't have any sides the same length. So that's false. They're not all similar. And then similar polygons have the same shape. Similar polygons have the same size. Same shape is true. They're just larger or smaller. It's just dilations. Same size, that is false, because like I just said, they're larger or smaller. So here we have a triangle with a line that's parallel to the base going through the inside of it, which cuts it into a lot of different proportions. We can say AB over AD, so we have the side over the whole length, would equal the other side over the whole length, AE. Because those triangles would be similar, we've got that proportion. AB over AC, so that's the left short side and the right short side over the left long side. So we would use the right long side, also AE. And then last we have AB over BD, just the top segment and the bottom segment. That would equal AC over CE, because they have the top segment and bottom segment. The question uses pretty much the same theorem, it's just the converse of it. If these lines are going to be parallel, then the sides have to be proportional. So that means x over 3.5 has to equal 15 over 5. So you cross multiply 5x equals 3.5 times 15, which is 52.5. And divide by 5 to find x equals 10.5. So this question is pretty much the same as what we did in number 8. The segment down here in the middle is going squared, equals the two lengths that it intersects with multiplied together. So x squared equals 18. Square root 18, and you get, you can round it to approximately 4.24. Just say 4.2 if you wanted to.